I will show how to create a virtual machine. This will be our first hands-on task using the virtualization software. And then we'll finish up talking about environments, particularly in the application development context. The relevance of that is that virtualization that gives us some interesting options for some of those environments. Okay, the first concept I want to talk about today is systems. So online people, this is going to be an interactive discussion. Tell me what you understand the word system to mean. Don't give me someone else's definition, just what do you think system means? You've all used the word plenty, you've seen it plenty, you're IT majors, so everyone please give me a short phrase. What is a system? Everyone who is online, please answer the question. What is a system? All right, keep typing your answer if you're still working on it. See some suggestions. John says a group of connected components. Stephen says a process for solving a problem. Quinn says it's some environment. Dean says it's a complex object. Dean, what makes it complex? Gilbert says something that completes a task. Okay, so some of these are very broad. Something that completes a task might just be a tool. Vin says it is a machine. Alvin says components working together. Mustafa says a system group of interrelated elements form a unified whole. Gulam, is that your own definition or did you get that from somewhere else? Quinn says parts interacting. Okay, so the one that I like there, I'm going to take Alvin's definition, different components working together. Dean says complexity is owing to circuitry. Okay, so when I say system in general, I'm not necessarily talking about a computer system. I'm just using the word in general. So a system is typically some collection of things. So it's a unified group, collection, set, whatever you want to call it. So we can look at it as one thing, and it typically has multiple components within it. A common model that we use for a system, particularly if we're looking at it from an IT perspective, but even broader, is that we have some type of process that is performed by the system, and the system has inputs and it produces outputs. So this input process output model is very simple, but often quite useful for analyzing a system from the external perspective. Particularly, we can talk about what are the inputs and what are the outputs, and we can describe the process at a high level. We can say what the system does. In order to understand it in more detail, we may want to get inside the system and understand what are the components. We may want to break it apart and see what are the pieces that make up the system. From the outside, we don't need to know how the system works. We simply need to know what does it do. If that is useful for us, we give it the appropriate inputs, we get the appropriate outputs. And we can use this not just for computers, we can use this much more broadly. We can talk about physical systems, we can talk about environmental systems, we can talk about it at the nanoscale, talking about cells or something like that, or subatomic particles. We can go to the macro scale, we can talk about how galaxies interact with each other and so on. So this is very, very general concept, very useful for helping us understand lots of different things. When we talk about computer systems, if we use that same model, now my system is saying it's forcing me to restart within 5 minutes. So I'll go for another few minutes and then we'll have to have a short interval while my system reboots. It's not letting me defer that. Okay, so we talk about a computer system. We use the same model. So we've got a computer. I like to draw computers like this, like an old-fashioned desktop computer, just a habit of mine. And we can talk about what are the inputs, what is the computer doing, and what are the outputs. In very general terms, what is a computer doing? So what is the process performed? We've got input, process, output. What is the process performed by the computer? Let me put a marker just to separate the answers. Go. Give me your suggestions. And please pay attention, I'm asking for your suggestions, not someone else's. Please do not give me answers that you find somewhere else. Give me your best understanding. What is the process performed by a computer? Go. Okay, so a couple of people say calculations. John says convert user input to machine executable code. Not loving that definition, John. The machine executable code is what the process is, the internals of the process. So that's how parts of it work inside. But particularly from the external perspective, what is the computer doing? I think calculations is a really simple and I think very old-fashioned answer to that question. Yes, it does things that may be calculations, but a lot of the things it does is not calculations. It's not just a glorified calculator that I would use to add some things up or give me the logarithm of some value or something like that. Dean is getting more into the internal. So again, I haven't asked you how does the computer work. I'm asking what is the computer actually doing? Quinn says receiving data. Okay, so data goes in, data comes out. So again, depends what kind of level we want to look at. It depends on our perspective. Quinn gave an answer based on what I said last time. I like to say a computer is a bit shuffling machine. So bits go in, bits get shuffled around, and bits come out. I think technically that is correct, perhaps not terribly useful in order to understand what you might do with a computer. If I was a non-computer person, you said that to me, I wouldn't understand what you mean by bits, or if you explained to me that it works with ones and zeros, I would say, well, that makes no sense. That doesn't help me at all. That doesn't help me find where I'm driving in my car or control the air conditioning or help me with word processing or find something online that I'm trying to do a Google search for or something like that. Dean says it handles data, turns it into useful data. Okay, so we've got data going in, data being processed, and data coming out. Data in the form of bits. Let's leave that for there for the moment. In a little more detail, let me just check what my next slide is. Okay, so yeah, I'm on the right track. So as we talked about last week, we can make a distinction between hardware and software. So if I draw the computer like this, and this is an abstract, the computer is not actually laid out like this. We've got hardware and software, and I tend just to draw the software box bigger because we spend a lot of time talking there. So at the hardware level, we've got things like the CPU, the central processing unit, which is doing sometimes calculations, but I think more often and more interesting than calculations is it's performing logic. It's doing things like testing values, saying, is this value 0 or is one value greater than another, in order to decide what should I do. It's not just performing step 1, step 2, step 3, where it always does this and then this and does this. What makes the computer interesting is its ability to do branching, to decide to skip over some instructions, or to iterate by going backwards in sequence in order to perform many instructions over and over until some condition is met. Alarm says receive data to perform arithmetic, store and transfer information into information. We talked last week about the distinction between data and information. Computers do not process information. Computers process data. Okay, so we need to understand that distinction. A computer is a data processing machine. Information is a human concept. Also in the hardware, we find memory, and the memory in this diagram, we can interpret the top part, this dotted line here, the memory we can lay out as what's above, and then we can talk about software as being mapped into memory. So oftentimes I'll use this diagram. We'll draw the software, where the software we represent as code to be executed and data to be processed. So there's code and data laid out in this memory, and often we're going to, for simplicity, just assume there's one set of memory. We'll think of it as being the RAM. We'll ignore things like registers and different levels of cache and so on. We've got hardware that takes inputs, and we've got hardware that sends bits to the outputs, and all sorts of different things. We talked about this last week. So we've got user devices, we've got networking, we've got attached storage and things like that. But in simple terms, bits come in from somewhere, we've got processing that occurs, and that may produce bits that go out somewhere. The hardware is fixed, but the state of certain components can change. So if we look here, particularly looking at the memory, the CPU is fixed. Let's ignore things like registers within it, but the CPU, you give it a bit pattern on the input and it produces a bit pattern on the output accordingly. The memory is variable. We can change its content, where we're not talking here about read-only memory. We're talking about, it's typically RAM. So we can change its contents, and that enables us to do meaningful processing on the data. We can change values, we can perform arithmetic on them, we can perform logical tests, we can do manipulation, things like rotations, masking, and things like that. We can move from one to another. We can do tests on values, so we can have a counter that counts down until it gets to 0 and then decide to do something else, for example. And all of these things at a low level, we then add layers and layers and layers of complexity and abstraction to the point where we can have the computer do things that we call things like artificial intelligence. We can have the computer appear to do things that mimic what a person would do given some data. The person would turn it into information and do something with it. We can have software that is designed to mimic that process. In some cases, do it as well, or perhaps even correctly and faster than people are able to do it. In other cases, of course, the software can't be very useful. There's certain things it cannot do because the software has no conception of what the data means. It's just a bunch of bits that are being manipulated by a tool. I think we talked last week about the inputs and outputs to the CPU. So we've got instructions or code. I'll put here I for instructions as well, just because we're using both terms. So we read an instruction into the CPU. Some instructions transfer data from memory to a CPU register. Some of them transfer value of a CPU register out back into memory. So these are the three flows in and out of the CPU. Some of the input and output devices are mapped to memory. So for example, the video display is treated as an area of memory, and it's write-only memory. You don't read the value of a pixel at a certain location, you just update the contents of the display. And we do that by writing to addresses that are mapped within the memory space. Other areas of memory like network buffers and things like that, we have data coming in that we can copy from one place to another into and out of memory. So the hardware devices manipulating data, most of which is stored in memory of some sort. If we look at a CPU from the perspective that we were just talking about, so here's our CPU, and let's go to our systems perspective. So the inputs are the code or the instructions. I'll use here I for instructions. We've got instructions going in. We've got data going in. And we've got data coming out. So that's our high-level view of what is happening with the CPU. If you give it a particular instruction and particular input, it will always produce the same output. At a very low level, in fact, we do one thing at a time. So an instruction might say to move data from an input location to a register in the CPU. Another instruction may say move register contents out into memory. And then we've got instructions that transform values in registers. So for example, we can increment the value of a register, simply add 1 to it arithmetically. We can do things like test the value and then decide what to do next based on the result of the test. So we can test, is this register value 0? If it is, do the next instruction, which might be a jump somewhere else. If not, skip over the next instruction. If we were to take a particular CPU, Quinn's asking, what does C stand for? C is code, instructions or code. So we're making a distinction between code and data. If we have a particular CPU, given a certain instruction, given a certain input, it always produces the same output. It is deterministic. There is no randomness or variability in the process. We want it always to give the same output for a given input and instruction. From the system's perspective, we don't know what is happening inside the CPU. And in fact, we could build different CPUs, and as long as they produce the same outputs for the same input and instructions, let's see, my system's going to reboot any moment. I may need to stop very suddenly. I'll let you know if I can. We could have different CPUs, and as long as they perform the same function, as long as they produce the same output for a given instruction and input, then we would say that those CPUs are equivalent. Now, one might be faster than another, one may use less power than another, there may be some differences like that, but in terms of functional correctness, do they produce the correct answers, let's put it in that terminology. If they do, then those CPUs are equivalent. What if we built a system and inside it, instead of having a silicon chip, it actually was a computer? And it was running some software that accepted instruction bits, accepted data bits, and produced output data bits. And if it performed exactly the same as a hardware CPU, we would say it's emulating the CPU. And this would not be difficult, it might be time consuming, but given the instruction manual, the opcode manual for a given CPU, most of you would be able to write some software to say, given these particular, this instruction, take this data value from here, put this data value there, perform this manipulation on it. So we could quite straightforwardly build software to emulate the processing performed by a CPU. And from a systems perspective, if it gave the correct outputs for the appropriate inputs, we would have to say it was functionally equivalent. And we might not even know what is going on inside our system. So the system could be hardware, could be a real CPU, it could be software emulating it, it could be something else. In theory, it could be a person who was sitting there and you give the person some bits, they look up the manual, they do the calculations, and they produce the output. So not practical, but functionally correct. Raise your hand if you heard the term Turing test. Okay, so a couple of people have, hands down. Okay, so the Turing test, this is, what was his first name? I think it's Ian Turing, I think it was a British mathematician and today we call computer scientist. Didn't have that term back then. Very, very influential. There's an award given annually. The Turing Award is given to someone in the field of computer science, and it's sometimes called the Nobel Prize for Computing because the Nobel Prizes don't have an equivalent one. Very brilliant researcher, developer, unfortunately persecuted because he happened to be homosexual, which at the time was not accepted by much of British society. That's kind of a sad story. There was a movie about him a few years ago. I don't remember the name of it. I didn't see it, but that brought his life to public attention. Anyway, he came up with a test, a theoretical test, where you write down a question. Let's say you've got a computer terminal, because in those days, let's go back 30, 40 years. So suppose there's a computer where you can type on it on the keyboard and you can see characters coming back. So you type questions on the keyboard and then answers are displayed on the screen. And you can interact with the system as much as you want. And then when you're ready, you have to decide if you are interacting with a person or with a computer. And the Turing test says if you cannot tell the difference, or if you guess incorrectly, then we would have to say that the computer was as intelligent as a person. I'm perhaps not using exactly the correct words, but that's the idea behind the Turing test. The reason I bring it up, if you were interacting here, if you were putting instructions and data in and the correct data was coming out, you would have to say that whatever it is you're interacting with was functionally equivalent to some hardware CPU, ignoring things like speed, energy efficiency, and things like that. So if we were to write software to emulate a particular CPU, look at the input, decide how to process it, perform the appropriate functions, and then produce the output, we would be emulating the functionality of a CPU. And that is something that's quite straightforward to do. And in fact, has been done in lots of circumstances. I worked on a project in the late 1990s to do exactly this. I was working at a division of GE, and we had old 36-bit CPUs on these large computers that were the next generation after early mainframes. In fact, some of them went back to the 1960s. And we had lots and lots of software, and we wanted to get it off this old unsupported hardware onto modern Linux systems, which were in those days 32-bit CPUs. I don't think we even had 64-bit CPUs then. So we were writing software to emulate the functionality of the 36-bit CPU onto 32-bit CPUs, which you can imagine is a non-trivial task. So emulation is about mimicking or reproducing the functional performance of, in this case, a CPU using software. Which brings us to virtualization. Virtualization is creating not just a CPU, but an entire computer, almost an entire, but let's just make it simple, creating an entire computer within software. So let's go back to our model that I had earlier. So I've got a computer and it's got hardware and it's got memory above. So this is the CPU layer down below. And this is the memory up here. And we can create within it a virtualized computer. Within the virtualized computer, it has its own virtualized CPU. So it performs the functions of a CPU. And we can virtualize the inputs and the outputs. So we can send data to it that looks like it came over, for example, a network, and we could send it to a virtualized network input. We can have virtualized hard disk storage. We can have a display and so on. So we can mimic or emulate the functionality of some computer entirely within software. And we call this a virtual machine. Don't know why it's not called a virtual computer, but virtual machine, VM, is the term that is commonly used. So here I've got a VM running within some software. And I'm going to keep skipping this So I'm going to draw a dotted box around it. There is some application running on the big computer, the main computer. And in this dotted box, there's a virtualization application, and it is running a virtual machine. And that virtual machine, we can make it whatever we want. We can have a certain amount of memory. We can have a particular type of CPU that we're emulating. We can have different peripheral interfaces and things like that. We can adjust the amount of memory that we allocate to it. And as long as functionally it performs correctly, then this can be extremely useful to us. One of the interesting things we could do is use a virtual machine of a different type from the main machine. So if we wanted to explore the functionality of a particular CPU and we didn't have a computer with that CPU, we could virtualize it in software and then run some tests to determine whatever we wanted to learn about it. And there's no reason why we're limited to one virtual machine. Let me squeeze another one in here. I'll draw a little one. We can have 2 virtual machines, or 3 or 4. M is for memory, yes. So here I've got one real computer and it's running an application, and in that application there are 2 virtual machines. And if the application supports it, we can have networking. So we could have these 2 machines connected to each other. I'll draw a connection here. So they're connected via a network link. If the application supports it, we can also do networking to the real computer. So I'll draw a link here and here down to the hardware. Diagram's going to get a little messy, but there's no reason why we can't have software to enable the real computer to communicate with any of the virtual machines. And Stephen said, can you have nested virtual machines? Sure, why not? If the virtual machine that you are virtualizing is capable of running the virtualization software or some virtualization software, then you certainly could nest this. You probably wouldn't do that because the overheads of the application would become more and more significant. So theoretically possible. In practice, I've not seen that, but you could. John says VMs aren't supposed to know that they're VMs. That is true. In 99.9% of cases, you don't need, the VM doesn't need to know anything about what it is. It's just a computer. It's just running software. It's processing inputs to produce outputs. Check what I've got next. Before I go to that, I want to come back here. So let me redraw this. And let's suppose we're running our virtualization application. I'll make it take up most of the memory. And then within that, let's put a handful of virtual machines. So we've got 1 real machine, 1 real computer, and 3 virtual computers. Dean, if you've got a question, go ahead. You can type it or speak it. That's okay. And so as we talked about, we can have networking. We can have these machines talking to each other. We can have the real machine talking to them. We could build some bridging software to allow external machines to talk to them, so they can use the networking to the real computer and have that kind of forwarded directly in. There's no reason why the virtualized machines have to be the same as each other, or even the same as the machine that they are running on. So they can have different amounts of memory, different peripherals. We can have different number of cores in a CPU and so on. There's lots of different options that we'll see when we get into virtualization. The difference between virtualization and emulation is important. If we are virtualizing, we've got our real hardware on the bottom with a real CPU as part of that. And we've got our operating system. There's a layer within the virtualization application, which I'll draw again in the dotted box. There is a layer at the bottom, and I'm going to call this here, I'll put HV for hypervisor. There is a layer at the bottom, and I'm going to call this here, I'll put HV for hypervisor. Hypervisor is a word that was made up. I guess it's hyper is more than, so we know the idea for supervisor. Well, this is even more than a supervisor. This is a hypervisor. The hypervisor enables virtual machines to get access to the real CPU of the real computer. So here I've got a virtual machine. Instead of emulating its CPU in software, which might be quite inefficient, in order to emulate one instruction in software, it might take me a few or even dozens of instructions, which is obviously going to be much, much slower. With a hypervisor, this enables the virtual machine CPU to actually be the real CPU. I'll just draw this arrow here. The hypervisor controls access to the real CPU under the control of the operating system. So we've got multiple layers of abstraction here, but let's ignore for the moment the operating system. So the hypervisor enables this virtual machine to have the real CPU take the virtual machine's data inputs, its code, and produce outputs from it. The hypervisor controls access to that under the control of the overseeing operating system, which we're not showing here. And if you've got multiple machines, the hypervisor determines which one gets access to it. So it performs some of the scheduling and management tasks that we talked about last time with operating systems. It makes sure that the machine doesn't access memory outside of its space and things like that. This enables us to get quite close to similar performance between virtual machines and real machines. If you think of, imagine the real machine is not doing much except running the virtualization application. So you're not running a whole bunch of other stuff. This machine is just doing this. And suppose there's only one virtual machine and the hypervisor is giving it most of the real CPU's time, then you could get quite close in performance to an actual machine. I'll just imagine maybe 80% or 90% efficiency. So it's somewhat slower than a real computer, but that may be acceptable. That may be enough for what you would want to do. So now the question becomes, why would you want to do this? What is it that virtualization gives us? And let's use this slide to talk about that. So for the moment, ignore the title. Okay, so what are the benefits of virtualization? Online people, give me your answers, go. Okay, Quinn says one host. Okay, so what is the benefit? Yes, there's only one host, but why is that a benefit? Maximum applications. Well, I can run also applications on the real computer. Alvin says less hardware. If I'm running multiple virtual machines on one, yes, that would be true. I can have one real computer running multiple virtual machines. So then the question, Alvin, is why is that an advantage? Why not just get, if I need 3 different things, why not get 3 real computers? John says it allows you to run other CPU architectures. Yes, John, hold that thought. I want to come back to that. Dean says you can run multiple operating systems on a single CPU, reducing hardware and reduce cost. Okay, yes, you can run multiple operating systems. So one of your virtual machines could be Windows, one could be Linux. And you can have both of those running together at the same time. Instead of having, I know some of you may have a dual boot system where you can boot your system up from a Windows partition, or you can boot it up from a Linux partition, but you can't have both at the same time. Here, you could have both of them. You could have the real machine running Windows, you could have the virtual machine running Linux, and if you had some particular need to use one or the other, then you could do both at the same time. Dean and Quinn are saying cost efficient. Okay, so what is the cost? What are we not spending money on? Gulam says we can segment larger network into smaller subnet efficiently. Gulam, I don't know where you're getting that from. We haven't talked about networks or segmenting networks. We're just focused on the machines at the moment, and we're just assuming that they can communicate with each other. This is not VLANs, this is virtualization. Okay, so Dean says additional computers, no longer necessary. Okay, so instead of having real computers, you can have a single computer and do multiple things on it. As long as it has enough resources to run multiple virtual machines, then certainly you don't need multiple computers. And it may be that the cost efficiency is such that having one large computer that supports some number of virtual machines is more cost effective than having multiple individual smaller computers, one for each of them. We get some flexibility in resource management. So you can have a large amount of memory and allocate a small amount of it to a small VM, a large amount to a larger VM. You can change that proportion between them. Let's see. Gulam says easily provide software updates rather than going to one physical computer at a time. Okay, so if you need to physically interact with something, so if you need to sit down at the keyboard and interact with it, yes, although these days with there's also different ways. A lot of maintenance we do by logging in remotely into computers rather than going to the actual console. So I'm not sure that's actually terribly helpful in most cases. Hugo says we can run multiple operating systems and applications on one server. Okay, so that may be cost effective. I'm going to say maybe. I'm not going to say it always is. Quinn says easier maintenance. Well, you've got one physical computer. I don't know what the maintenance is. If you're talking about hardware maintenance or software maintenance, software maintenance probably not much difference. The hardware, I don't know if people do much maintenance these days. Stephen says we can sandbox software to check for malware. Okay. John says malware can escape VMs. Quinn says better security. I really want to discourage you guys from just using the word security. You guys are in the cybersecurity concentration of the IT major. So when you're talking to other IT security people, saying good security is like saying do good stuff. It's really imprecise. So Quinn, I think we need to there are lots of different aspects to security. You need to be a lot more detailed about exactly what you're talking about. John says good deployability, so you can send an exact copy of your environment to others. Yes, we're going to talk about environments in a moment. Okay, so Stephen is saying we can sandbox the software. Okay, so if we have a virtual machine, we can do testing within it, and if we have some malware that ends up corrupting that environment, we haven't corrupted a real computer, we've only corrupted something that's running in the memory of the real computer. So we can just throw it away instead of having to rebuild a new computer. If you've got a real computer and you get malware that causes a bunch of problems, you may end up having to reinstall the operating system from scratch. That can take quite a long time. It can take, literally hours of clock time. Someone's going to have to do that work and keep an eye on it. So that can be quite time expensive in order to do that. So for experimentation, for testing of things, particularly if we're concerned that there might be malware or other issues related to that, we can use VMs. And VMs have an advantage that they are quicker to stop and start. You can think, if you think of a VM as running essentially it's in the memory of the real computer. you can snapshot its state. So you can suspend it, you can copy that memory to disk, write it out to a file. And later on, if you want to restore it, you simply copy from the file back into the memory state of the virtualization application, and you just pick up exactly where you were. You can have multiple copies of that. As John said, you can send a copy to someone else, and they can pick up not only your environment, they actually pick up the same state that you were in. You can have something that's already booted up and running. I'm sure you all have the experience. Every now and then your computer goes, it does an update and takes forever, and then it wants to restart, and you're waiting minutes and minutes and minutes. I did one the other day. It took 20 minutes and doing all these update cycles, and I was trying to do something urgently. It was very frustrating. With a VM, you can do that once and have that VM at the state where it's all ready to go, and then you can copy that and put it onto multiple machines, and they're all absolutely identical. They're all starting from the same point in virtual time in the life cycle of that VM. And Gulam says take snapshot for testing. Okay, so we take a snapshot not just for testing for weakness, but so that we have a known good state. If you boot your virtual machine up, you get it into the state where it's ready to go, and then you snapshot that. If it gets corrupted, you can then restore it back to that state very quickly just by reloading from a file, which is much quicker typically than rebooting an actual computer and going through the entire boot process. So one benefit, one reason we use virtualization is the speed of bringing systems up, in particular restoring systems if there's an issue. If there's something going wrong, we can very quickly go back to a known state very quickly in time, go back to a